Okay, so we've talked a little bit about the impact of excluding important regressors, right? That results in bias. And now let's dig down a little bit further in this other phenomenon that if we include unimportant regressors, that causes so-called variance inflation. So I'm going to show this with a little simulation. Okay, so in this case I have a sample of size 100 and I'm going to do 1,000 simulations. So let me define those. Get some space down here so we're just looking at this new set of code. Okay, so I'm going to define those, and then I'm going to define 3 regressors. They're all just 3 independent random normal vectors. And then what I'm going to do is I'm going to simulate data where the outcome y only depends on x1 and error, and then doesn't depend on the other 2 variables. And then I'm going to look at the standard error for the x1 variable for the model that just includes x1, the model that includes, that's this one, the model that includes x1 and x2, that's this one, and the model that includes x1 and x3. And I'm going to do that over and over again, and I'm going to look at the standard deviation of the simulated estimated coefficients. Now the reason I'm doing this by simulation is because the variance inflation occurs on the actual standard errors, not the estimated standard errors. It's actually a little complicated in that if I put another variable into a regression model, it doesn't necessarily inflate the observed standard error. And the reason is because the variance is estimated rather than the actual variance. And that has a kind of conflicting property. So you don't necessarily see the variance go up when you include a regressor in a regression model, an unnecessary regressor into a regression model. And so you have to look at it through simulation. So let's go ahead and do this. And this is sort of the ideal setting where the 3 regressors don't have anything to do with one another. Now, what you see is, in fact, so the first model, this is the standard error, the standard deviation of the beta coefficients I got across all simulations. Here's the second one. It actually went down a little bit for the second one. Now we know theoretically that can't happen, but there's some Monte Carlo error when I do my simulations. So let's just say these 2 are about the same. And the third one is also about the same, 0.032 as opposed to 0.031. So nothing that bad. The variance inflation by including the extra variables did almost not, was negligible. And the reason that is the case is because these other 2 variables, x2 and x3, have nothing to do with x1. I simulated them independently. Let's look at a case now where I've simulated them in such a way that they depend heavily on x1. So I'm going to generate my x1 as I did the last time, just as a random normal vector, but my x2 depends on x1, but also some noise, and my x3 is heavily dependent on x1, very dependent on x1. Okay, so now let's repeat the simulation and see what happens to the variability in the estimated coefficients. Okay, now we see huge amounts of variance inflation, especially for this third model where we include x2 and x3, right? We see the standard error has gone up by a factor of 5. Okay, and that goes to the general rule. If the variable that you include is highly correlated to the thing that you're interested in, right, you are going to inflate the variance more. And so you need to concern yourself with putting highly correlated variables into your regression model unnecessarily. Okay, so if I have diastolic blood pressure in my model and I put systolic blood pressure in my model, which is basically the same, relatively the same thing, they're very correlated. If I did that unnecessarily, that's going to make my diastolic blood pressure standard error, it's going to increase it. So yeah, so imagine, for example, another example is if you had height in a model and then you also included weight or something like that, something that's highly related. Height and weight tend to track pretty well with one another. And so if that was necessary to include, then you just have to bite the bullet and deal with the extra standard deviation, the extra standard error that you get. However, if it's unnecessary, then you don't want to include it. So again, the main point is the more correlated the regressors are to the regressors that the covariates are to the regressors that you're interested in, the worse off you're going to be in terms of paying a penalty for increased standard deviation. So that goes to show there's no free lunch. If we omit variables that are important, we get bias. If we include variables that are unnecessary, we inflate standard errors, especially if we include variables that are unnecessary that are uncorrelated with our variable of interest. And this again reiterates why randomization is so important, right? So it randomizes across these other variables, the known and unknown knowns that we would otherwise need to include in the model, so that we can only include the treatment effect of interest. And things that we include, even if we feel like we have to, they should be relatively balanced or relatively uncorrelated with the treatment effect because it's been randomized. And so we won't get this kind of variance inflation that we would get otherwise. So again, that's why randomization is such an important quality. Okay, now let's talk about variance inflation factors. So we don't know the actual sigmas, so when we include, so we can't actually calculate the exact variance inflation. That depends on the actual true residual variance. However, if we can compare ratios of them, the sigma would drop out, and then we can create things like ratios of variance inflation that accurately represent how much the standard deviation is inflated or not. So there's a particular measure that is very commonly used in regression called the variance inflation factor, or VIF. And all this is the comparison, this ratio, the variance inflation that occurs from what you actually have, looking at the standard error for the data that you have, versus the ideal setting where all the other covariates that you were interested in are orthogonal to the covariate that you're interested in, or uncorrelated. Let's just say uncorrelated. Okay, so remember that was the ideal case, right? So if everything else was uncorrelated to what you're interested in, we didn't see much variance inflation. So this looks at the case that you're in versus the ideal case where what you're interested in is uncorrelated with all the other variables. That's the so-called variance inflation factor. And here I give a little simulation. I'm not going to show it, where I just show you that the ratios can get estimated, and I show via a little simulation that they can get estimated pretty well. So let's actually look with the Swiss data. Let's look at the variance inflation. So what I'm going to do is fit the model. Oh, sorry, here it is. I'm going to fit the model with all of the variables included. So when you do a tilde dot, it includes all of the variables. And then I'm going to do VIF of fit. That gives me my variance inflation factors. Oh, but you have to remember to load this library CAR. Okay, let's load that. And then now let's try it again. And I would rather than the variance inflation factors, I would look at the inflation factors for the standard deviations, which is just the square root. So let's look down here. So on the first line, I have the variance inflation factor by itself, and then in the line below it, I have the square root of it, which I tend to prefer. So let's look at the first line, just because it's the more normal thing, the variance inflation. So the agriculture one is 2. What does that mean? It means the standard error for the agricultural effect is double of what it would be if it were orthogonal to all the other regressors. Okay, and we see that some of them are quite high. Examination is quite high, 3.67, so almost 4 times than the instance if it were orthogonal to all the other regressors. And we know that examination and education are highly related, so that's why these two have very high variance inflation factors relative to some of the other ones. And you can see, take a variable like infant mortality, right, which has a very low variance inflation factor. Infant mortality is largely going to be unrelated to any of these other variables by and large, and so you can see that it doesn't have a large variance inflation factor because it is pretty much unrelated to the other variables anyway. Okay, so that's gets you a little bit of headway into the world of looking at what happens when you include unnecessary variables. And one of the ways to look at that is so-called variance inflation factors, and they're incredibly useful little tools, and I hope you get a chance to use them. So up to this point, all that we've talked about is the impact of unnecessary or necessary included variables on our regression coefficients. But there's one other parameter that we estimate in a regression model, the residual variance, sigma squared. So what happens if we have, assuming IID errors, and that our linear model is additive and that part of the model is correct, then we can mathematically describe the impact of omitting unnecessary variables or including unnecessary variables. And it follows along the same lines as what we discussed before. If we underfit the model, in other words, we omit important variables, then the variance estimate is biased. Why is that? Because we've attributed to variation things that are actually systematically explained by these covariates that we've omitted. On the other hand, if we either correctly fit the model, we include all the right terms, or if we overfit the model, then the variance estimate is unbiased. However, the variance of the variance estimate gets inflated if we include unnecessary variables. So it's actually kind of the same rule. If we omit, as we discussed before with coefficients, if we omit variables, then we get bias. If we include variables, then we get a less reliable estimate. So it's roughly the same impact going on. So let's talk about model selection in general, automated model selection. And I just want to briefly mention again that automated model selection is something that we cover in the machine learning class. It really, I think, at one point it was a statistical topic, but it's really moved into the realm of machine learning for the most part. And I would say though, even for relatively simple linear regression models, the space of model terms that you have to search among explodes really quickly when you start including interactions and polynomial terms like the square of a regressor and so on. If you have a lot of regressors and you're interested in how do I reduce this space, then there's a lot of factor analytic and things like principal components, those kinds of techniques that are available to you to reduce your covariate space down to size. Now, however, those come with consequences. Your principal components or factors that you obtain might be less interpretable than the original data that you're interested in again. Again, this is probably better served in a multivariable class, a multivariate class, or a class on machine learning. But for us, we're going to mostly consider the case where we have a relatively small number of regressors, and we're going to pick through them with a highly interactive process between the analyst, the data, and the scientific context. Another thing I would mention is that good design can often eliminate the need for a lot of this model discussion. We've talked a lot about how randomization can really prevent a lot of the problems that we're talking about with making our variable of interest unrelated to nuisance variables that we're not interested in or nuisance variables that we don't even know about. However, there's other aspects of design that can serve the same purpose. For example, if we stratify and randomize within strata, the classic example of this, when this was developed, was R.A. Fisher was working in field crop experiments, and they needed, let's say you're trying a different kind of seed, you might block on different areas of the field that you were going to plant in and randomize the different seeds to those areas. So you might have two different kinds of seeds, but they will have been distributed in a systematic way that is fair across the field, but also then within that design there will also be some randomization. This topic of experimental design is a pretty broad topic. Another great example is in biostatistics, the field that I work in the most. A very common kind of design is a crossover design. And in that case, you try to use every subject as their own control. So let's say, for example, you're interested in looking at two different kinds of aspirin. and you might give the aspirin to one group of people and then the aspirin to another group of people, the other aspirin to a different group of people. Let's say they have different gels or whatever that determine how it gets absorbed in your stomach. So if those two groups aren't the same, either the randomization wasn't very good and there was some sort of imbalance that you just got unlucky about, or if the study was just observational, then the comparison of those two groups might be biased by whatever differentiates the groups, rather than group 1 receiving one kind of aspirin and group 2 receiving a different kind of aspirin. On the other hand, if you can give a person one kind of aspirin and then later on give them a different kind of aspirin when they have another headache, that would compare each person to themselves, right? Control block on the person, so to speak. So that's a design strategy. Now there's some nuance with this design strategy as well. What happens if there's some residual effect of the first aspirin when you give the second one, right? So maybe you could handle that with some sort of washout period, a long washout period or something like that. But anyway, the point of that design is to make it so that you're comparing people with themselves to control and everything that's intrinsic to the person, at least across time periods, control for that by giving both aspirins to each person. Maybe you would randomize the order in which they receive them. That's called a crossover design. At any rate, the broader point that I'm trying to make is it's often the case that good, thoughtful, experimental design can really eliminate the need for some of the main considerations that you'd have to go through in model building if you were to just collect data in an observational fashion. The last thing I would say is there's one automated search technique, model search technique that I like quite a bit, and I find it very useful. And it's the idea of looking at nested models. So I'm often interested in a particular variable, and I'm very interested in how the other variables that I've collected will impact it. So I'm interested in a treatment or something like that, some important variable, but I'm worried that my treatment groups are imbalanced or with respect to potentially some of these other variables. So I might look, what I'd like to look at is the model that just includes the treatment by itself, then the model that includes the treatment and, let's say, age, if the ages weren't really balanced between the two treatment groups, and then one that looks at age and gender, if maybe the genders between the two groups weren't really balanced, and then so on. And this idea of creating models that are nested, every successive model contains all the terms of the previous model, leads to a very easy way of testing each successive model. Okay, and these nested model examples are very easy to do, so I'm just going to show you some code right here on how you do nested model testing in R. So I fit 3 linear models to our Swiss data set. The first one just includes agriculture. Let's pretend that that's the variable that we're interested in. Okay? And then the next one includes agriculture and examination and education. I put both of those in because I'm thinking they're kind of measuring the same thing. But now, after this lecture, I'm concerned over the possibility that they're too much so measuring the same thing, but let's put that aside for this time being. And then the third model includes examination, education, plus Catholic, plus infant mortality, so all the terms. So now I have 3 nested models, and I'm interested in seeing what happens to my effect as I go through those 3 models. The point being, in this case, you can test whether or not the inclusion of the additional set of extra terms is necessary with the ANOVA function. So I do ANOVA, fit1, fit3, and fit5. Okay, that's what I name them, 1, 3, 5. And then you see down here what you get is a listing of the models, model 1, model 2, model 3, and then it gives you the degrees of freedom. Okay, that's the number of data points minus the number of parameters that it had to fit. The sums of squares, the residual sums of squares, and then the excess degrees of freedom of going, DF is the excess degrees of freedom of going from model 1 to model 2 and then model 2 to model 3. So we added 2 parameters in going from model 1 to model 2, that's why that DF is 2. And then we added 2 additional parameters going from model 2 to model 3. So the 2 parameters we added from going from model 1 to model 2 is we added examination and education, their 2 regression coefficients. Going from model 2 to model 3, we added Catholic and infant mortality, their 2 regression coefficients. Okay, so with this residual sums of squares and the degrees of freedom, you can calculate so-called F statistic and thus get a p-value. This gives you the F statistic and the p-value associated with each of them. And then here it shows that yes, the inclusion of education and examination appears to be necessary over just looking at agriculture by itself. And then when I look at the next one, it says yes, the inclusion of Catholic and infant mortality appears to be necessary beyond just including examination, education, and agriculture. Okay, so if the way in which you're interested in looking at your data naturally falls into a nested model search, as it often does, I think, when you're interested in one variable in specific, as in this case, I think this would be a pretty natural way of thinking about the series of analyses, then some kind of nested model search is a reasonable thing to do. It doesn't work if the models that you're looking at aren't nested. For example, if I had the first model, or model 2 had examination but not education, and the third model had education but not examination, this wouldn't apply. You'd have to do something else. And there I think you get into the harder world of automated model selection with things like information criteria. So I would put all that stuff off to our prediction class and then just leave you this one technique that's useful in the one specific instance where you've decided to kind of look along a series of models, each getting increasingly more complicated, but including the previous one. Okay, so I hope in this lecture that you've gotten a couple of model selection techniques that you can use. I hope you've also learned that there's some basic consequences that occur if you include variables that you shouldn't have or exclude variables that you should have. These has consequences to your coefficients that you're interested in. They have consequences to your residual variance estimate. We didn't even touch on some other aspects of poor model fit that can occur, such as absence of linearity and other things like that, non-normality, and so on. So again, it's generally necessary to take your model fits with a grain of salt because more than likely one aspect of your model is wrong. And I'll leave you then with this famous quote by George Box, who's very famously said, all models are wrong, some models are useful. And I think that's a very good credo to go along with that. Yes, for sure your model is wrong, but it might be useful in the sense of being a lens to teach you something useful and true about your data set. Okay, so that ends today's lecture, and I look forward to seeing you for the next one.